In this video presentation, we shall be talking about the relationship between the volume of any gas and the number of molecules in the gas, or better, the number of moles in the gas. Now, this lesson also meets part of the assessment criteria that you have for your learning outcome 10, part 10.3d. Let's now move on to the specific learning outcomes for this video lesson. So in this lesson, we shall be learning how to calculate the volume of any gas, okay, produced at STP. I shall also explain what STP is in the next slide, okay? Suffice to say at this point that STP means standard temperature and pressure. So we shall calculate the volume of any gas at standard temperature and pressure given the amount in grams, for example, of one reactant in a chemical reaction. Or we could work the other way around. If we are given the volume of the gas produced at STP, then we could also calculate the original reacting mass of that reactant. Now we shall explore this by means of a typical example soon enough in this presentation. We shall first rather define Avogadro's law. Avogadro was an Italian scientist who in 1811 formulated a hypothesis that will be the basis of this presentation. I shall go into more detail about this in the next slide. However, a word of caution, if you do a search, a web search, you will find it referred to either as a hypothesis or as a principle or as a law. I have just been looking at a very authoritative textbook which is currently being used also with advanced level chemistry, and the reference is to a hypothesis, okay? Don't let that confuse you. Just be aware that it is possibly called by various names, okay? Let's now move on to the next slide, where we shall give the background about Avogadro's principle. So as I said in the previous slide, in 1811 Avogadro formulated his hypothesis. Now what exactly did he say? He said that equal volumes of gases. Now let's take a typical example. An equal volume of a gas could be, for example, 100 mils of hydrogen gas. Okay, so if we have 100 mils of hydrogen gas to give something tangible and realistic, and if we have, for example, 100 mils of, I don't know, let's take ammonia gas, okay, so NH3. So we have two equal volumes of completely different gases. Now, if we were to measure the volumes of these gases, 100 mils of hydrogen and 100 mils of ammonia, at the same temperature and the same pressure, there will be the same number of molecules. So what I'm saying is this: if at temperature, let's take the temperature to be 273 Kelvin, okay, or 0 degrees Celsius. Remember that both hydrogen and ammonia are gases at that temperature. So if I take the temperature to be 273 Kelvin, which is the same as 0 degrees Celsius, and I take the pressure to be 1 atmosphere, it's atmospheric pressure in the room that you are in right now. 1 atmosphere is also the same as 10 to the 5 pascals. They are different units. And when I say 1 atmosphere of pressure, it is exactly the same pressure as 10 to the 5 pascals. I chose those units and I presented them in that format because that is the way that you will see them for MedSec examination. Now, if I have 100 mils of hydrogen at those conditions of temperature and pressure, and I have 100 mils of ammonia also at those conditions of temperature and pressure, there are the same number of molecules of ammonia as there are of hydrogen. In other words, if I keep the temperature and pressure conditions constant, any gas measured under those conditions will have the same number of molecules. So if I had, for example, 1,000 mils of hydrogen at 273 Kelvin and 1 atmosphere of pressure, it will have exactly the same number of molecules as will the same volume of ammonia under those conditions. Okay? We can go further. Let us say that we have a volume equivalent to 22.4 liters or 22,400 mils. Under those conditions, okay, of standard, so we call them standard temperature and pressure. So I introduced the conditions of standard temperature and pressure without saying what they were. Okay, so do know that when I am talking about a temperature of 273 Kelvin and 0 degrees Celsius, that is standard temperature. Standard pressure is 1 atmosphere or 10 to the 5 pascals. So, if I had to have a gaseous volume, it can be any gas, okay? It can be any gas. And that gaseous volume is equivalent to 22.4 liters. Decimeters cubed is the same as liters, okay? Now 22.4 liters, as you well know, is the same as 22,400 mils, okay? So if I had to have that gas volume under conditions that are equivalent to standard temperature and pressure, therefore 273 Kelvin and 1 atmosphere of pressure, I will have 1 mole of a gas in that volume. In other words, I will have 6.02 times 10 to the 23 molecules of that gas. Now, do not get confused. If I have 22,400 mils or 22.4 liters of hydrogen gas, under those conditions, standard conditions of temperature and pressure, it will contain 1 mole of H2 gas. In other words, it will contain 6.02 times 10 to the 23 molecules of hydrogen. If I have 22,400 mils of ammonia gas or 22.4 liters of ammonia gas, also at standard temperature and pressure, therefore also at 273 Kelvin and 1 atmosphere of pressure, it will also contain the same number of molecules, 1 mole of gas, 6.02 times 10 to the 23 molecules. Therefore, we say that the volume of gas, okay, that is at STP and is equivalent to 22,400 mils is the molar gas volume. The molar gas volume is the volume of gas at STP that contains 1 mole of molecules. Okay? Now, we can use also a very simple equation, okay, which I have indicated over here. Now, all of this will be easier to understand when we give an actual example. And as in maths, the more examples you work out, the easier this will work out to be as well. So remember what we said. If I have 22,400 mils, okay, so I'm going to highlight that once more over there, okay, of any gas. If I have 0.5 moles of a gas, since 22,400 mils is the volume taken up by 1 mole of any gas, so 1 mole of any gas at STP has that volume. Therefore, if for example I wanted to measure the volume of half a mole of gas, it can be any gas, it can be hydrogen, ammonia, hydrogen chloride, fluorine, any gas you like. If I had to measure the volume of half a mole of gas, it will be half as much as 22,400 mils. In other words, my answer would be 11,200 mils. Of course, I could also make the 0.5 moles subject of the equation, and I could find the number of moles of any gas if I am given its volume. So if I am given the volume, listen, I have 11,200 mils of hydrogen at STP. How many moles of gas are there present? And the moles of gas present will be the fraction 11,200 all over 22,400. Why? Because 22,400 is equal to 1 mole. Therefore, by simple proportion, 11,200 mils must be half as much. If, for example, I were given, I don't know, 2,240 mils, okay, that would be 1/10 the volume. So since it's 1/10 the volume, I would expect to have 1/10 the moles. So instead of 0.5, the answer would work out to be 0.1 of a mole of any gas. Now it's very important to note this. I've put it in italics over here so you don't get confused. If you are going to use mils to describe the volume of 1 mole of molecules, okay, then make sure that in your numerator the unit that you use is also mils to describe the particular gas volume that you are dealing with. Likewise, if you are using decimeters cubed or liters in your denominator, then you should use decimeter cube also in your numerator. Okay, make sure that you use the same unit throughout. Okay, I strongly suggest that you review this slide after having seen the next one, because all I've said here will be so much clearer after you've seen an actual worked example. We shall now give an example in order to illustrate, okay, to show clearer what the full meaning was of what we discussed in the previous slide. First of all, I will read through the test question. We are being asked to calculate the volume of hydrogen gas at STP, and the unit we are being asked to use is in mils when 15 grams of zinc granules react with excess sulfuric acid. Now, it is important to note that in such a problem, such a test question, we first need to write out a balanced chemical equation, okay? And the balanced chemical equation is already provided to us, as is the solution to the question, okay? So make sure you get your balancing revision up to date. Zinc granules, okay, will react with sulfuric acid. Note the ratio is 1 mole is to 1 mole throughout. So if I have the zinc reacting with H2SO4, it's in the ratio of 1 mole is to 1 mole, and the hydrogen produced is also 1 mole, okay? Now, I've also included a little picture over here of a typical gas setup that could be used if the gaseous volume is very small, okay? You wouldn't use such a setup typically if you are going to collect the volume of gas that we have in this in this problem, okay? In this problem, the eventual volume of gas is this big, okay? Typically, gas syringes would have a volume of no more than 100 mils. So if you're going to use such a setup, you'd either have to use a larger gas syringe, but even so, your volume of acid, your concentration of acid, and your amount of metal sample must be far smaller than what we have indicated in the problem, in the test question. The first thing to do is, when solving such a problem, is to look at the part of the question that gives you the most numerical information. And it is this part of the question where we have 15 grams of zinc granules. Now, as we many times do when solving calculations in chemistry, we need to convert the mass into moles, because after all, the only way that we can use the chemical equation for means of a calculation is by making use of the mole ratio. We know that the mole ratio is 1 mole throughout. So what we do is, as always, we look at the relative atomic mass of zinc. It is 65, and we know therefore that 1 mole of the metal, 1 mole of zinc, will weigh 65 grams. Okay? It weighs 65 grams. Remember what we said in previous presentations, okay? That the relative atomic mass converted into grams is the mass of 1 mole of that substance. So 1 mole of zinc will weigh 65 grams, but we only have 15 grams of zinc. So it will work out to be less than a mole, okay, by simple proportion. Okay, that part is worked over here. Look, we're 15 on 65. It works out to be 0.231 moles of zinc. So we now know that we have 0.231 moles of zinc, and since the mole ratio is 1 mole throughout, we must therefore be producing 0.231 moles of hydrogen. Now, as we said in the previous slide, 1 mole of any gas at STP, okay, so 1 mole of any gas at STP has a volume equal to 22,400 mils, okay? Note that in this test question, we are being asked to give our hydrogen produced in mils. Now, do we have 1 mole of hydrogen produced? We have less. We have just 0.231 moles of hydrogen gas. So clearly, okay, the volume of hydrogen gas will be less than 22,400 mils. It will be about 1/5 as much. And when you calculate that, okay, using that calculation right here at the bottom, it works out to be a volume of 5174.4 mils of hydrogen gas as measured at STP. So that's the solution. Now be aware that the question could have been asked in a different way. The examiner could have asked you to calculate the mass of reacting zinc granules, given that the volume of hydrogen at STP was this much. So in which case what you do is you'd work in reverse. You'd first determine the moles of hydrogen gas, and you'd find the moles of hydrogen gas to be 0.231 moles. Since you would still have the chemically balanced correct equation in front of you, you would know that the reacting ratios throughout are 1 mole is to 1 mole is to 1 mole is to 1 mole. So if you have 1 mole of hydrogen, you must have started off with 1 mole of zinc. If you have 0.231 moles of hydrogen, you must have started off with 0.231 moles of zinc. So you would then determine the number of zinc moles, and knowing the number of zinc moles, then of course you could easily calculate the mass to be 15 grams using this sort of relationship. You would say 0.231, you would say 1 mole of zinc weighs 65 grams. Okay, how much does 0.231 moles weigh? So as you can see, you could be asked the question given the hydrogen volume, and you are being asked to determine the mass of the reactant. It works both ways, okay? You can either calculate forward if you like, or you can calculate backwards. Now, I strongly suggest that you go through the presentation all once more, because all of it will be much clearer and much more understandable after you've been through this example. And I also strongly recommend that you look up test questions relating masses of reactants to to the volumes of gases produced and working through them and checking out your working and your answers with your class teachers. Thank you for watching and have a fine day.